Thank you so much for coming. It's been really a great pleasure to meet with so many different people over the past 2 days. I was originally supposed to just come and give the DeFord lecture, and then I found out about the Cheer seminar series, and it's really awesome that both could work out. So today, as Gita mentioned, I'm going to discuss the role of mountains in understanding and simulating Earth's climate. This is work I've been doing in some form since my PhD, though I'm going to talk mostly about work that's happened since I've been a professor at UC Irvine. If any of you happen deep in the pandemic to tune into a Zoom seminar I gave at UT, the first paper I'll be discussing overlaps a little bit with that seminar, but I have to get through it for the rest of the work I'm going to present to make sense. So hopefully it'll be a nice review and I won't be boring you. Okay, how do I... Okay, there we go. So as Gita mentioned, my group works on a couple different topics, trying to not let it become any more than it currently is. I do this work on mountains and climate. I'm trained as a climate modeler, so a lot of this is running sort of novel simulations with numerical climate models. But I also do some somewhat more applied work about tropical cyclone with risk and heat risk. I discussed the heat work yesterday, so feel free to reach out to me about either of these other topics as well. Yesterday, I was discussing projecting heat health impacts in a changing climate. Today, I'm going to be addressing these more kind of fundamental climate dynamics questions that really segue into how we build our climate models to say something reasonable about Earth's climate in the present and projecting into the future. So, just as some very broad motivation to start, regional precipitation remains highly uncertain in the future of climate projection. This is a plot pulled from the IPCC AR6 report, where it's shading the percent change in precipitation relative to pre-industrial, pulled from a bunch of climate model simulations. And where it's stippled, it shows, or like crossed, that's conflicting signals, and where it's dashed, that means there's no change or no robust signal. So basically, for many parts of the world, we're still pretty confused about what's going to happen to precipitation. And, you know, I used to live on the East Coast, I live on the West Coast now, and it's just so clear when you're living in Southern California that if there was even a rather small change in the amount of precipitation that was being received, it could have drastic effects on sort of the livability and ecological habitability of that climate. Part of what contributes to our trouble understanding what's going to happen with future regional precipitation is that the climate models we are using to understand what will happen with precipitation have recalcitrant biases, basically meaning they have trouble simulating precipitation in the present. So if you have a tool that has trouble simulating the present, where we actually know what precipitation is, it makes it more challenging to have confidence in what's going to happen going into the future. There's a bunch of different precipitation biases that people focus on, but probably the most famous one is what's called the double ITCZ bias. ITCZ stands for Intertropical Convergence Zone. It just means the strong bands of precipitation in the tropics. And what's shown in this figure is the difference between model simulated precipitation from a range of climate models minus observed precipitation. And the top panel is like a couple generations ago of climate models. The middle panel is a somewhat more recent generation, and the bottom panel is the current generation. If you focus in on the Pacific, those patterns of precipitation bias look pretty darn similar across those generations. So we've spent a lot of effort to improve climate models, and yet this bias persists. And in particular, what this bias is in the Pacific, you tend to have more precipitation in the north than the south, and we have an anomalously large amount of precipitation in that southern rain band compared to what we actually should have, and this has knock-on effects for how for example, climate variability might evolve into the future because if you've heard of the El Nino Southern Oscillation phenomenon, that really stems from what's going on in the Pacific. So people are attacking the issue of climate model biases from all different perspectives. And today, the sort of hammer I'm going to focus on is what's going on with mountains with regard to these climate model biases. And the reason why one might think they have a role is that mountains drive key aspects of both local and large-scale climate and play a particularly significant role in some of these regional precipitation patterns. Carrie Cook's in the room, so I needed to show a figure from a study she worked on a while ago looking at the kind of basic circulation patterns that are set up from mountains. So in this case, this is an example of a plot where they're looking at an idealized sort of Gaussian mountain in a somewhat more simplified climate model. So people have been looking at the role of mountains using climate models, going from like rather simplified models to now today. I've done work and others with these much more sort of high resolution models that are not mostly climate models, but bridging more into Earth system models where you have land, atmosphere, ocean that are all interacting. And so in this case, you're seeing a plot of what happens if we run a simulation with the Tibetan Plateau and other topography in Asia, and then another simulation where we don't have that topography at all. So it's sort of like, I describe this as kind of like playing God. I'm crushing these mountains and seeing what happens. And when you look at the precipitation output from those two experiments and take the difference, you can think of that as what is the impact of uplifting Asian orography on climate. So you can get a sense of some things that are pretty well known at this point. For example, you see this big increase in precipitation around the Himalaya and sort of the Asian monsoon sector. There's a lot of literature demonstrating that the Tibetan Plateau and the Himalaya play a role in the Asian monsoon. You also have these more remote effects, though. You have this drying of Central Asia, which has actually been pretty robustly connected to Asian mountains. But then if you look at the western U.S., you even have some robust precipitation changes occurring over the western U.S. And that's because the atmosphere has these waves that form that can transmit signals from one continent to another. And that's part of the reason why sometimes it's valuable to run these simulations with global climate models. Though Carrie and I were just talking about other situations where, really you could be running a regional model and get a lot of the effects you're interested in as well. So one of the main mechanisms for orographic influence is mechanical blocking of the atmospheric circulation. I say one of the main mechanisms because the reality is there's a variety of ways in which mountains impact Earth's climate. They have thermal effects that can occur. Mountains actually play a really big role in river routing, which I'm completely neglecting here. But what I mean by mechanical blocking is simply if you imagine a scenario where you have winds flowing towards a mountain, in what I describe as a low blocking scenario, the mountains are relatively low relative to the strength of the wind, so the winds can effectively go up and over the mountain. In a high blocking scenario, the mountains are really kind of blocking that wind such that the wind has to sort of change direction and divert around the mountain or even begin to be reversed. And so the issue in climate models is that due to limitations in their spatial resolution, this mechanical blocking by orography is likely underestimated. So stepping back, you need another piece of context about climate models, which is that the typical spatial resolution of these global climate models used for, global warming projections tends to be about 1 degree, sometimes as coarse as 2 degrees, sometimes as high resolution as 25 kilometers to 50 kilometers. And you do read about simulations that are approaching a few kilometers in scale, but it's really still hard to have the computational power to run those simulations over the whole globe for long periods of time. So if you think about the complexity of Earth's topography and putting that on a, say, 1 degree grid, what ends up happening is you have, say, imagine this is a real mountain. It's obviously a cartoon. In a typical GCM simulation, what you're doing is you're averaging that topography across the grid cell to put it in, and when I say GCM, I just mean global climate model. Apologies if I forget and say that. So you put it in just as the average across the grid cell. And if you think about this in areas with kind of steep topography, this is going to result in the topographic peaks not being well captured. Now, I was aware of this issue for a while, and I decided it would be interesting to figure out a way to just do a sensitivity test to see how much this mattered. And so we came up with this experiment I'm going to describe as high topo, where we do kind of the most extreme thing we can do in the opposite direction, which is rather than taking the grid cell average, so the average of actual topography over a 1 by 1 degree, say, grid cell area, making that the topography that's in the model. Instead, we take the maximum height of the topography over a 1 by 1 degree area. So we're basically capturing the peak height of the topography, but, effectively we're going to have more topography than we should at high elevation, basically. And the hypothesis we're overall going to test over the next series of slides I'm going to show is that high topo in GCMs better captures the mechanical impacts of orography and improves climate simulation. Now, I should say, actually, when I started doing these experiments, I was viewing it more as a sensitivity test. I frankly have been surprised by how much this can improve climate model simulation in a way that might be usable. But again, it's an interesting way to at least probe the fact that we have significant biases in climate models due to the incomplete resolution of topography. So I'm going to have two slides on some methodological details that might be a little bit boring for those of you who aren't in climate modeling land, but bear with me, I'll be through it in a second. So over the rest of this talk, I'm going to compare results from 3 different global climate models, or GCMs, in various observed data sets. The 3 GCMs we've worked with are GFDLCM 2.5 FLOR, which I'll just abbreviate as FLOR after this. It has a relatively high resolution, 50 by 50 kilometer atmosphere and land, and somewhat lower resolution 1 by 1 degree ocean. We also looked at CCSM4 simply because I had a collaborator who happened to have run some relevant simulations, Alyssa Atwood. This was run with a 1 by 1 degree approximately atmosphere and land resolution and a 1 by 1 degree ocean. And then because we ended up getting funding by NASA, we used the GIST model, which in some climate modeling circles is famously bad, but its biases look a lot like what you see for the average across climate models. So for our purposes, it still was useful. Anyway, the GIST model actually has about 2 degree atmosphere and land resolution, so much coarser resolution. And then we compare to various precipitation, wind, ocean current, and sea surface temperature data sets. Some other methodological details I'm going to blaze through, but basically we run all these simulations with pre-industrial radiative forcings. So there is nothing in here where we're thinking about global warming. We're just thinking about under like a constant radiative forcing, what is the climate that these models simulate. These are atmosphere-ocean coupled models, so we have to run all these simulations for a while. We run them for about 200 years, and then we throw out some of the years at the beginning because we need to account for model spin-up. I'm going to show a bunch of plots where you'll see some white areas. Those are areas where we basically masked out data where the difference is not statistically significant between the 2 simulations. And then this is probably the most important part. So like, if you're going to pay attention to something on this slide, pay attention to this. So I'm going to show a lot of results that are plotted as perturbation simulation minus the control simulation. So this is a simulation with elevated topography minus a simulation with standard topography. And you can think of this as what is the influence of raising orography better capturing those peak heights on climate. Now, if it's improving model resolution, then that model simulation, then that plot should look a lot like a plot of the observations minus the control model simulation. So often when you're calculating model bias, you take the model simulation and subtract the observations. minus 1 times that is what our target will be for these simulations where we've elevated topography. If those two plots look similar, that means that we've reduced the model biases. I'm going to generally show results for March, April, May when discussing some assay with Central America, and December, January, February for North America, which are the seasons with just the worst biases for these respective reasons. And I want to note that the model parameterizations are tuned for the control simulations, but not altered from the control tuning for the perturbation simulations. This is an important point I'll return to at the end, but suffice it to say, when a modeling center is developing a climate model, there's actually a pretty significant tuning process that goes in before they release a model for prime time use. So it's a little bit unusual to modify the boundary conditions and not retune the model, but you can think of that as it's just an even harder test for the model, arguably. Okay. So we employed boundary conditions with standard orography and this grid cell maximum orography, which I refer to as high topo. So this is topography in the real world. This is in our floor control simulation. This is in our high topo simulation. The interesting thing to look at is the high topo minus the floor control. So basically everywhere that has complex topography, when we're using this grid cell maximum topography is higher, especially around, again, you can see like the Andes, the Himalayas, the Western US. There's some weirdness that happens in Antarctica. This has to do with a combination of after the fact adjustments that are made to the topographic boundary condition, and also we think some model grid versus observed grid issues. But anyway, everything I'm focusing on is in the tropics, so this is not a very big deal. Okay, so first I want to give you a sense of the zonal maximum surface height in Central America. So zonal maximum means that we're taking the maximum across longitudes in the plot I'm about to show. So we're taking the maximum across the longitudes over this box, and on the y-axis is latitude, and x-axis is latitude, y-axis is surface height. And what you see in the black line is the observed topography from a 5-minute resolution data set, so relatively, well, there are much higher resolution topographic data sets, but this is much higher resolution than the climate model. Then we see in blue the control climate model simulation. And the thing to look at is that the black line and the blue line, there's a significant difference there because, again, we're not capturing those topographic peak heights. So you can think of that as like, that's evidence of, maybe we're not blocking the circulation enough. Our high topo experiment is shown in gray. It's showing up as dashed red and gray in some places because two lines are overlapping. And you can see that in that experiment, we're much better capturing the zonal maximum surface height of the topography. The dashed red simulation is just an experiment where rather than elevating topography everywhere in the world, we just elevate it over Central America. And then we have these two experiments with this other model, CCSM4. The control is shown in turquoise. It's even lower resolution than floor, so the difference with observations is even larger. And then this was actually a simulation that was run originally for a different purpose, so it's a much more idealized elevation of Central American topography. You can see the difference between the turquoise line and the pink line. It's just a lot higher on the pink line. But we use this to better understand some of the mechanisms that are going on. The results end up being surprisingly similar. Okay, so first, finally getting into results. So top line, raised Central American orography first reduces wind and sea surface temperature biases in the tropical East Pacific. So what this plot is showing on the top left is biases in wind and floor in the top panel and CCSM4 in the bottom panel. It's really -1 times the biases again. So where it's blue, that's indicating that the wind speed is too strong. And so what you can see is in kind of the lee of the Central American mountains, these easterlies are just blowing too strong into this region. So the winds, easterly means blowing from east to west. Those winds are blowing too strong through Central America, which might be evidence, again, of the topography being effectively too low. So what's shown in the bottom panel is on the top part is the results of the experiment where, again, we elevated topography everywhere in floor, and you can see a strong reduction in the easterly strength in this northeast tropical Pacific, which pretty well mirrors where we have this bias in the control simulation. So that's a strong amelioration of this bias. We find that almost all of this change, though not 100% all of it, is coming from Central America. That's shown in that G panel there. And then, interestingly, much of this pattern is captured in the more idealized experiment with CCSM4. So this is basically saying, even though we do this somewhat complicated way of elevating topography, if you just crudely elevated topography over Central America, you see a similar effect. Now, sea surface temperatures also tend to have this bias where they're too cool in GCMs in this region of the northeast tropical Pacific. That's evidenced by that red blob in the eastern part of the basin there. And similarly, in these experiments, we see a warming of SSTs because basically the easterlies are weakened, so we've reduced the latent insensible heat fluxes from the surface, and we also reduce the ocean upwelling, which further cools SSTs. Okay, so I focus mostly just there on these local processes that are driving the change in sea surface temperatures. These are atmosphere-ocean coupled simulations, though, and so something that was really interesting that we found is that there are actually biases in the ocean circulation itself that were improved when we were better capturing the height of Central American topography. So an issue with the GFDL model is that the north equatorial countercurrent strength, they could never capture very well. So these observations, see that like red line going across the Pacific, that's the north equatorial countercurrent in observations. In the floor control, you can see it's too weak. And then in the high topo simulation, it's significantly strengthened. And most of that strengthening is captured by the experiment where we've just uplift Central American topography. You can see this. This is a plot just looking at the zonal mean of those currents, where the peak there is the north equatorial countercurrent. And we can explain this by looking at the changes in wind stress curl as a result of the mountains as well. So I motivated this talk by precipitation. I've kind of meandered away talking about winds and SST for a while, but it matters because the SST patterns play a big role in driving precipitation over the Pacific. And what we find is that following these circulation SST improvements, the raised Central American orography leads to more realistic tropical East Pacific precipitation. So again, this top panel is showing what the biases are. On the right-hand side, that's just what the mean precipitation is in these simulations. So you can see, again, this rain band in the South Pacific that if you look on the right-hand side, it's too strong. Where it's red, that's saying there's too much rain. And we actually have too little rain in the northern Northeast Pacific. And then, again, in our simulations, the raised Central American topography helps significantly reduce these biases. So raising this topography leads to more precipitation in the Northeast tropical Pacific and less precipitation in the Southeast tropical Pacific. I should note that while this pattern matches the bias, the effect in terms of how much it ameliorates the bias is higher in the Northeast tropical Pacific. In the Southeast tropical Pacific, it's pulling things in the right direction, but there's definitely more to the story there. Maybe topography is part of it, but it has to be interacting with some issues with, say, parameterizations of clouds as well, which is something that's frequently discussed with regard to the double ITCZ bias. So, one final thing that was interesting in these simulations is to look at what happens to simulation of ENSO. So the floor model, if you look at this plot, focusing on this like sub-panel within the plot for a second, if you look at the standard deviation of sea surface temperatures associated with ENSO in the black bars, you compare it to the blue bar, which is the floor control. There was this issue with the GFDL model where its ENSO variance was too high. basically. And when we have the elevated topography, both just over Central America, in fact, over the whole world as well, we gradually tamp down that ENSO variance, which is consistent with just, there's a lot of literature showing that if you improve your mean climate simulation in the Pacific, you tend to improve your simulation of El Nino as well. And similarly, there's this issue with the GFDL model where if you compare the blue, so the x-axis in these seasonal plots here is a month of the year, and the y-axis is basically another measure of the ENSO variance normalized. And what you can see is there's this strong sort of seasonal phase locking of when there's more variance from ENSO, that's shown in gray from a few different data sets. And this is a more slight result, but the model developers claimed to me they were very happy and this was a significant change. But this blue line here is the control simulation. It just really wasn't capturing the seasonal phase locking very well. And with the elevated topography, even though the amplitude's still off, we're beginning to capture this variation better. So, okay, so that brings me to, I'm now moving past some of what I discussed in that seminar, deep in the pandemic, to why I wanted to bring you through that again. So, shortly after that seminar, I was funded by a NASA New Investigator Award to basically continue this work. The key questions we're interested in addressing are, first, what are other regions with major biases from underestimated mechanical blocking of topography? We had focused on Central America and the Pacific, but obviously there's complex topography in many other regions. What were other sort of candidates that we should be paying attention to? Another question is, well, we ran these experiments as an interesting sensitivity test, basically. We were candidly somewhat surprised by how much they tended to reduce these model biases, and that led us to wonder, you know, is this just an interesting way of noting that there are significant biases in GCMs driven by topography, or can these sort of thoughtful modifications of the topographic boundary conditions be a usable way to reduce model biases? And then finally, how does this topography-related uncertainty compare to that from model parameterization? So if you read literature about climate models, some of the major issues that people talk about are the fact that with climate change, what's going to happen with, say, cloud feedbacks, for example, is really critical. However, all those clouds, or most of them, are happening at scales that are much smaller than the GCM grid cell size, and so we might not be able to simulate them well. And there are many other processes that fall into that category. So, you know, these topography-related uncertainties, how do they compare to those from model parameterization? So are they like way, way smaller than those issues from model parameterizations or not? So I've had two group members who have done a great job helping me with this work over the past 2 years, whose work I'm going to cite here. One is Jared Sexton, who is my PhD student, and Durva Megan Kumar, who's a postdoctoral researcher. And we've also been collaborating heavily with Greg Alsacer, who is at NASA GIS. Okay, so we recently submitted this paper to Journal of Climate, which is focused on the Western US. And we were motivated to look at this region because, somewhat like the Pacific, there are rather consistent biases in precipitation over the Western US. So this is a plot from a study of CMIP 5, which is the second to last generation of global climate models. And the x-axis, these are all different global climate models. And the y-axis, if you're above the orange line, it's basically saying there's too much precipitation simulated over the Western US. And the green dots show the summer, the blue dots show the winter, and all of those blue dots are above this orange line. So across all GCMs, there's too much precipitation simulated in the Western US. And that's true in the winter. It's mostly true in the summer, though there are some exceptions regarding the summer bias. Now, here's a map showing the Western US wet biases in CMIP 6 in winter. And so this is now the most recent generation of climate models. And Still, you can see where it's red, there's too much precipitation simulated, and that's remarkably consistent across all these different climate models. The magnitude of the bias and the pattern specifics vary, but overall there's too much precipitation simulated. And interestingly, there tends to be, for not all, but many of the models, too little precipitation simulated over the southeast US. So there has been prior work thinking about the cause of these biases, and a major culprit that's been targeted is sea surface temperature biases. So there's this good paper by Nat Johnson where basically he takes the floor model, that GFDL model I introduced in the last part of the talk. He runs standard simulations with it, and he runs what are called flex-adjusted simulations, where basically it's a way of reducing the sea surface temperature biases, among other things. And what you see, if you focus on the left-hand side of this plot, is in the standard simulation, you're simulating too much precipitation in the western US. And then in the flex-adjusted simulation, you're still simulating too much precipitation in the western US, but it's significantly reduced, basically. So part of the story is probably these sea surface temperature biases. But after doing that initial work on Central America and just looking at a topographic map of the US, it's natural to ask, well, is it possible that the complex topography over the western US is playing a role here? Do overly smooth mountains in the western US also drive precipitation biases? And so, we had these high topo simulations ready to go, and so we started analyzing them. So just to focus in on what things look like over the western US, this is observed topography. This is the difference in topography between our high topo simulation and the control simulation. So you can see that surface height is higher, again, as you'd expect in the high topo simulation, especially over places with relatively complex topography. So I'm going to cut to the chase of the core result, and then I'm going to describe some of the physical mechanisms. But essentially, we find that raised topography, so basically better capturing mountain peak height, does indeed substantially reduce the western US wet bias, especially in winter. So this is a plot showing now the mean across that, remember that plot that looked like all the stamps? If we take the mean across all of those, this is -1 times that mean bias. So basically it's still saying there's too much precipitation simulated over the western US, and the black stippling is showing places where more than 80% of models agree on the sign of the bias. This is the bias or -1 times the bias in the control simulation. And so just to make the point that the floor control simulation, its bias looks pretty similar to the CMIP6 model mean bias, in that you have too much precipitation over the western US, too little precipitation in the southeast US. And then this is the effect of raising topography over, in this case, over the whole world. And I'll talk more about where this change is coming from. But you can see this remarkable similarity in the pattern of the precipitation bias, or -1 times the precipitation bias, and the change in precipitation from elevating the topography. So both in terms of the magnitude and the pattern, which is basically saying that by this sort of crude way of better capturing the effects of the mountains, we're able to substantially reduce the precipitation biases over the western US. And I won't talk about this as much today, but there's also some improvement over the southeast US as well. So immediately wonder, okay, so how do we understand this change that's occurring? Now, if you think back to that plot I showed of the Tibetan Plateau earlier in the talk, remember there are these changes in precipitation that can reach all the way in the western US from the Tibetan Plateau. So it's not obvious that this change is stemming from the Rockies. So we ran some simulations where we raised more particular sets of mountains to figure out what was the main driver here. So this is the plot I just showed. It's the effect of raising topography everywhere on these biases. This is a plot where we raised topography only kind of north of Mexico, basically, over North America. And you can see that not all, but most of this precipitation bias in the western US is stemming from the local topography, or the reduction in the precipitation bias, rather. And then this is a plot where we're adding the effects of the change from the Rockies and change from raising Central American topography. And basically, so there's some additional effect of Central American topography. Interestingly, the Tibetan Plateau does also contribute to this bias reduction. I'm not showing this here, but there is some degree of improvement that comes from that far field as well. But the bulk of the story comes from this local topography. So, to understand how these mountains are driving this drying, we did a moisture budget decomposition of this region. So basically, we're looking at how much of the change is coming from changes in, I think it's easier if I just cut to the results of the moisture budget decomposition. So this is a way of thinking about when you see a change in precipitation, how much is coming from changes in the mean flow and mean humidity versus how much is coming from changes in transients, like storms, for example. We find it's a pretty even 50-50 split between changes drying due to changes in the mean flow versus changes in transients. That's shown on the left-hand side of this plot. Now, we were able to do a further decomposition of this mean flow term into how much of the change is coming from changes in humidity versus changes in the wind, basically. And the story is a bit more complicated here, but top line, basically, it's the dynamical changes, so the changes in the circulation that are leading to the drying. So, if you look at mountains force, again, these large-scale wave patterns. And if we look at the stationary wave pattern, so the change in the large-scale circulation, this is here at 200 millibars, but the lower level in the atmosphere basically echoes this, forced by the topography. We basically see this high-low pressure pattern lining up along the western U.S., which results in this basically anomaly flowing from east to west over the western U.S. So this basically is reduction in the westerly strength. And you can think of this as mattering for that drying over the western U.S. because basically we're ejecting less moisture in from the Pacific because of this reduction in the westerlies, the mean winds that flow from west to east in this region due to the topography. And if you go back to kind of early studies decomposing drivers of stationary wave patterns, this stationary wave pattern looks quite similar to studies that have looked specifically at the stationary wave pattern from the Rocky Mountains. So even though we're elevating the Rocky Mountains, we're not removing them wholesale or something like that. The general pattern is quite similar. Again, the transients play a strong role too. So this is a plot looking at the change in western U.S. storminess, basically. And you see this strong role, especially like before the topography gets really high in reductions in storminess. And we think this can be explained by basically the very sort of local blocking effects of the topography. So, and sorry, it keeps getting cut off at the top. So the story here, I mean, we've been focused on topography, but the proximal issue, or not the proximal issue, the root of that issue is that the models are too low resolution, right? And there have been experiments that have focused specifically on if you run the same model at low resolution, high resolution, what happens. High-res MIP is this model intercomparison project, which basically means lots of people ran different simulations and contributed to it. And so an interesting way to, while it's hard to run this kind of simulation, lots of different global climate models, we can use high-res MIP to begin to test the hypothesis that these mountain biases matter in other models. So what this plot is showing is on the x-axis for a range of different kind of models contributed by different modeling centers. We're plotting on the y-axis the bias in the western U.S. box. And the large, basically the size of the square is showing, reflects the resolution of the model simulation. So when the square is bigger, it's lower resolution, and when the square is smaller, it's higher resolution. And I want to flag that the EC Earth Consortium, I'm pretty sure that data is just totally corrupted, because if you look at the plots, it doesn't make any sense. So maybe ignore that one. But if you look at the rest of them, you can see that about 10 out of 14 of the high-res models show a reduction in Western US precipitation bias with increased model resolution. So it's not perfect, but it does point in the direction of, again, our hypothesis that incomplete resolution of these mountains is leading to these wet biases in this region. Okay, so, you know, as you can see, at least from the GFDL model, this seems like a pretty good way of potentially reducing model biases, or at least pointing to the fact that topography is playing a big role in the model biases. But again, I was funded by NASA, so we wanted to run some experiments with the GIST model. And so the first thing we did was we said, well, let's just do the exact same thing in the GIST model as what we did in the GFDL model. Let's calculate grid cell maximum topography, stick it in the model, turn the crank on the simulation, and see what happens. We were a little naive in doing that because what we ended up doing was completely shutting down the Atlantic meridional overturning circulation initially. So this is a plot showing in the control simulation from GIST E2.1, which again has a 2-degree atmospheric resolution, so it's much coarser resolution. And what's shown here is Atlantic overturning circulation strength at 2 different latitudes in green and blue. And in the control simulation, it kind of like goes up and down, but stays somewhat constant with variability. This is what happened in our high topo simulation. So it's just like crashing, no more overturning circulation. And it's sort of funny, when I show these results to different people, they have very different responses. Model developers say, well, the model wasn't tuned properly, clearly. And then you talk to the paleo people and they're like, maybe this is interesting. But anyway, I won't get into that more. But my postdoc, funny part of this story is she's great. She comes from more of a paleo background, so she came to me with those plots and was like, wow, this is really looking like some past climates I've studied. I'm like, okay, that's not good. That's not a good thing. So we went back to the drawing board and said, okay, like, what's happening here? And what we landed on, which maybe is obvious, but wasn't obvious to us from the beginning, was that if you're making these modifications to the topography, the appropriate way to do it is going to heavily depend on the model resolution. So what's shown here is over the western U.S. The left-hand side is the observations of topography. Middle is what's in the control model, and the right-hand side is this like max boundary condition. And you know, you can kind of argue like which one looks more like the observations. Well, they're both in the realm of maybe reasonableness. In contrast, in the GIST model, when you calculate the grid cell maximum topography over these much larger areas, you end up with these, like basically turning the Rockies into a plateau that results in a much stronger stationary wave pattern, which changes things in the North Atlantic and ultimately ends up leading to shutdown of AMOC, which is not what we want to happen. Then we're like not on Earth anymore. We're in some other situation. So what we then went to was, okay, rather than just making random assumptions, is there some way we can try to be like a little more quantitative with how we're creating these boundary conditions? And what we ended up doing was using something called the Froude number as a dynamical constraint, or trying to use it on topographic boundary conditions. So the Froude number is used for a lot of different things in atmosphere and ocean dynamics. In this context, I'm using it as a way to quantify orographic blocking. So basically, you can think about how much blocking you're going to have as resulting from a ratio of how stable the atmosphere is, how high the topography is, and how strong the winds are. So when the winds are stronger, you're less likely to have blocking. When the atmosphere is more stable, you're more likely to have blocking. And when the topography is higher, you're more likely to have blocking. And so you can sort of think about this low and high blocking scenario as a lower Froude versus higher Froude scenario. What we ended up doing, and I'm not going to show all the boundary conditions here, was we tried a whole host of different ways of formulating these boundary conditions. Some where we took, like, rather than the mean or the median, the 90th percentile or the 70th percentile of the grid cell topography. We also tried this thing called envelope topography, which is actually a very old technique. It goes back to, like earlier weather models, where basically you take the mean grid cell mean topography and add one standard deviation of the grid cell to it. And so you're capturing the mean and then like some variation of that topography, but it's encompassed in one value in the end. So very coarsely thinking, flow is going to be blocked when your Froude number is much higher than 1. Oh no, this is why whenever you're giving a seminar, don't embed PDFs in the slide. Okay, good. Okay, so on the left-hand side is the eTopo 5 topography. This is the observed topography again. And what we're showing here, though, is not in terms of surface height, but we're calculating Froude here. And then what's shown in this bar is basically a sort of, I think it's the zonal maximum of the Froude number across the Andes. And that weird, it looks like a color bar, but it's actually not, to the right-hand side of the panel. Okay, so then look at the control simulation, and you can basically see when you're black, the flow is almost certainly being blocked. When you're getting in sort of the white area, it's more ambiguous if the flow is going to be blocked or not. In the control simulation, that kind of white, like green area is too large relative to the observations. In contrast, in our grid cell maximum topography scenario, that black area is way too large. We have too much blocking. And so what we found through testing a bunch of different boundary conditions is this envelope topography thing seemed to be sort of a good sweet spot, at least for the Andes. We're capturing some of this white area. And indeed, when we use instead this envelope topography in GIST 2.1, it does improve Pacific and South American precipitation. So this is -1 times the model bias in the GIST model. And this is the change in precipitation from elevating the Central and South American topography. So generally we make things drier in the Southeast tropical Pacific. We also resolve some of the biases over South America as well. However, it's not perfect, especially there are some major issues when you get into the deep tropics. And we think that part of the issue actually pertains to interactions with the cloud parameterization. So in short, if you look at the circulation changes in these simulations, so this is on the left-hand side, the -1 times the bias in the circulation. So the circulation is going too much like this. So if you're reducing the bias, it should be going more like that. We do get a circulation going like that, but it's shifted a little too far south. And we think that part of the reason the circulation change isn't moving as far into the tropics as it should is that the GIST model version we're using, the newer version, which we've now started using because it's now been released, has better clouds, but this version has a real strong bias in the low-level clouds that we think feeds back on the circulation changes due to topography. So the next step of what we're doing with the GIST model, it's kind of the final part of this grant, is we're using GIST E3, which is the better and newer GIST model, and we're retuning the model parameterizations using this machine learning technique, which I'm happy to talk about in more detail. If you're interested, it's pretty hot off the press. My collaborator, Greg Seltzer, used it, but what's cool about it is it allows us to begin to ask that question of how big is the uncertainty from the resolution of the topography itself versus these model parameterizations. And so we're going to try to answer the question, how much can we improve a GCM by simultaneously optimizing the topography in this way in parameterizations? And think about, do different topographic boundary conditions lead to different optimal phase spaces of the parameterization settings? Parameterizations are kind of a dark art, and those of you who are not climate modelers might find this sort of uninteresting, but when you're getting into the nitty-gritty of the uncertainties of climate models, it's important to think about this a little bit. Okay, so to wrap things up, Relatively small orographic features can have quite large climatic influences contingent on their placement relative to the larger scale circulation. I bring that up not as that wasn't really the focus of this talk, but it's clear from the results from the Central America experiments where these relatively small mountains have a big impact because they're like the easterlies are running right into them. The limited resolution of global climate models results in overly smooth and low topographic peaks, underestimating the mechanical effects of topography. Interpolating topography to preserve peak heights helps resolve persistent Pacific and Western U.S. GCM biases in circulation and precipitation. However, this appropriate interpolation strategy is heavily resolution dependent. We demonstrated that food number might provide a dynamical underpinning for creating boundary conditions that capture mechanical blocking. However, I think we're still far from saying, well, every modeling center should try doing this. It's one attempt in this direction. However, I think really this method is kind of distinct but complementary to ongoing efforts to solve these problems via improved parameterizations of convection, clouds, and ocean processes. Of course we need to keep improving those parameterizations, but if we're not doing so while being mindful of the biases from incompletely capturing the topography, we might go off in the wrong direction. So anyway, that's it. I have some collaborations with paleoclimate researchers around mountains and climate I'm happy to talk about if you're interested, but I'll wrap up there for time. Thank you.